Okay, so oh, maybe I can do that. Okay. Now we try it again. All right, so I'll go back to Okay, so chapter 5 is stereochemistry, and we started talking about that last time. Okay, so here is 2-butanol. Remember that when you want to draw something in 3D, I didn't say this earlier, that you need to have lines. The lines mean that you are in the plane of the board or the paper. The slash means you're going back, and the solid wedge means you're coming out, okay, forward, okay? So I don't really want to take those apart yet. Well, here, we'll use this. I'll stick something on here so they're different, okay? So here I'm holding the methyl, and you've got the OH coming out and an H going back, and this chlorine and this methyl are in the plane. Okay, so you see how that translates to this. That's really important because we're going to be doing a lot of looking at things and thinking about how they look in 3D. If you've been thinking about buying a model kit, this is the time to go buy it. Okay, if you want to try to do it without a model kit, there are some alternatives. Okay, gumdrops and toothpicks can work. Okay, some people have used those colored marshmallows and toothpicks. They had better luck with that. The good thing about those things is that you can eat them when you're done, but you can't really make big molecules with them, okay? But you can get your chiral center figured out, okay? And we'd already used the term chiral last time, okay? What did chiral mean? It doesn't have a plane of symmetry, and what this molecule is going to make, because it doesn't have a plane of symmetry, is mirror images that are, what was the word? Non-superimposable. Okay, those words are going to be on the slide. Okay, so there's my mirror image. So remember, everything has a mirror image except
vampires.
Vampires! Thank you, Jessica. I wanted that in the video. So when Caitlin watches it, Caitlin, when you watch it, I want you to tell us that you learned about vampires. Okay? Okay. When you have non-superimposable mirror images, those are called enantiomers. Big words in this chapter, enantiomers. So remember, I've got two molecules. Look here. Make everything match up, okay? And they are mirror images, but I can't superimpose them. I can't put them together. If you go like this, that's not superimposing. That's just making the mirror image again, okay? Superimposing means you put them together and everything matches up. Here I've got a chlorine and a hydrogen that don't match up. Those are non-superimposable mirror images. So it's important to note that an enantiomer is not just a mirror image. It's a non-superimposable mirror image, okay? Because you can have a lot of molecules that have, every molecule will have a mirror image. So here's my mirror image. And then look what I can do. I can superimpose it and all four things match up, okay? Okay. Stereoisomers are isomers that have the same constitution but differ in spatial arrangement of their atoms. And we had talked about stereoisomers before when we talked about cis and trans and double bonds and rings, okay? And enantiomers is a new category in stereoisomers, okay? These are both 2-butanol. The OH is on carbon 2. That's where it's coming from. We're going to get to that nomenclature. But they're both 2-butanol, but they're not identical. Okay, they only differ in one simple little way. Okay, but that's real important. Okay, These compounds are called chiral compounds. Chiral compounds do not have a plane of symmetry. So if I took this and I took my molecular knife and I went, and I cut it in half, okay, is not the same. This side has an H and this one has a chlorine, okay? If I took this one and took my molecular knife and went, and I cut it in half, okay, I've got methyls on both sides, right? They sound like that too. Okay, so this compound is chiral. This one is not. It is called achiral, A-C-H-I-R-A-L. I'm sure that's coming. Okay, here. This is 2-bromo-2-chloropropane. Okay, so notice we've got the 2 methyls in the plane, the chlorine going back, and the bromine coming out. Okay, I make its mirror image. Well, these 2 are superimposable on each other. They are achiral compounds. They are the same thing. It's the same molecule drawn 2 times. The other thing wasn't the same. Okay, all right, so surely I've got the word achiral on this slide. Okay. Achiral compounds have a plane of symmetry. Okay, and remember what we talked about, that was a way to help you find them is you look for a carbon that has 4 different groups attached to it. Okay, the carbon on this slide that's in the middle has 2 methyl groups on it. That's the same. If one was an ethyl and one was a methyl, it would be chiral. Okay, so you have to look at the whole thing that it's attached to. Okay. Okay, here is the 4 groups. So notice that this is what we refer to as a chiral center. A chiral center has 4 different groups attached to it. Okay, and you see that we put that little asterisk there? That stands for chiral. It's like a standard that you'll see when in this chapter in the book, they'll talk about this and they'll show you the chiral centers and they'll put little stars by it, little asterisks. Okay, this carbon, excuse me, has 2 methyl groups. Okay, chiral centers are also called asymmetric centers, because there's no symmetry at that spot. Stereogenic centers or stereocenter. So if you ever had to write a paper that had that, you got plenty of synonyms to use. Okay, I don't know why there's so many terms for it, but there are. It's kind of wild. All right, you get them all written down? Stereogenic, okay? And this is real important because we are chiral. Okay, we are made up of amino acids and all these molecules that have these chiral centers in them. And if we eat the wrong one, it can kill us. Okay, it could also, if we eat one, it can kill the bacteria in us and not kill us because we use different amino acids. Okay. Note, the word carbon can be used in place of the word center. So we'll call that a chiral center, but we'll also call it a chiral carbon. Okay. So you could have an asymmetric carbon, a stereogenic carbon. I don't think I've really seen stereocarbon used though. Okay. But the other 3. Okay, find the chiral carbon. So back to our why we study this. Okay, this is a compound that's called limonene. It's found in lemon oil. All of these are naturally occurring compounds on this slide. Okay, that's limonene. Okay, where is the chiral center? I'm going to tell you there is one. Okay, so can you find it? Limonene is also found in other citrus fruits as well. Where is the chiral center? You can't get sick, it's not allowed. Nobody can find a chiral center in langbeinite? Where is there 4 different groups attached to a carbon? That carbon right there. Okay, what are the 4 groups? You got this double bond methyl thing. What else you got? A hydrogen. So if you need to draw in the hydrogens, draw them in so you don't forget where they are. Okay, but what about this ring? Well, as you go around the ring, do you see that it's not symmetrical? If that double bond had not been there, it would not have been a chiral center. Okay, so when you run into a ring, go around the ring and see if it's identical all the way around.
So it doesn't matter what carbon's directly attached to?
No, you have to look at the whole molecule. The whole molecule. So as you go around this ring, you go CH2s, and then you go here, and here's a CH2, and over here is a CH, and a double bond. So they're different. If that double bond hadn't been there, you would have had this. And it's this. Okay, and that would not be a chiral center because as you go around the ring, it's the same, identical.
So what makes the carbon with the double bond to the methyl not?
Because you have to have 4 different groups attached to it. If you're a double bond, what is that carbon's, it's not tetrahedral, it's trigonal planar geometry, so you can slice it through the plane. Okay, yeah, if you have a double bond, those things are, even if you had 4 different things on your double bond, okay, which we can do. Maybe. Okay. Look, I use all my colors. Ooh, ooh. Okay, so here's this. Okay, why isn't that a chiral center? Because do you see the plane of symmetry? It just fell off. Here, I'll just hold like that. So you just cut all those atoms. Okay, because it's trigonal planar. Okay, what's the difference between cis and trans? Same side, opposite side of the double bond because you can't rotate. So that's a little bit different than this. This is non-superimposable mirror images. If I made the mirror image of this, I could just flip it around and it would match up. Okay, because there's symmetry through all those atoms. Okay, I don't have enough of those colors. I only seem to have 1 of each color. All right, look at this one now. Look at that one. That compound is linalool. It's from orange flowers. That's right. Okay. So where is there? There's a chiral center. I'm telling you, there's a chiral center in every one of these. Okay, so where's the chiral center? Which carbon? Not one. Be specific. The one with the OH. Good. Okay. So what are the 4 different groups? We have the OH. And what do you have up here? A methyl. And then you have this whole big thing. And then you have that double bond. Okay. Those are your 4 different groups. See what you're looking for? Okay. How about this compound? And we know what that is? You heard of that? Adrenaline? Just a little? Okay, there's a chiral center. I told you there was one. Where is it?
Is it the one with the OH?
Yep. Because it has the OH, it has the CH2NH, okay, it has that whole group. It has the whole benzene ring thing, and then it has another H, okay? So like I say, if you need to on the sticks, draw them in. Do you see that this carbon has no H? Okay. Okay, none of these down here can be chiral because it's flat. Okay, because it's all sp2 hybridized carbons, trigonal planar. Okay, how we doing? Is it sinking in yet? All right, how about that one? And we know what that is. Have you heard of histidine? Find a chiral center in histidine. There are amino acids that have more than one chiral center in them too, but this one only has one. Okay, which one? Be brave.
The one with the amino or the amine.
Yep, that one. The one with the CH, you've got the amine, you got the H, you got the CO2H, and then you got the whole thing down there. The CH2 and that fancy ring. Fancy ring.
So all the amino acids are chiral except for glycine.
Right, because it has two H's. It's CH2 is glycine, yeah. Okay, where are the chiral centers in the molecule below? Now, I'm hoping that this is going to work. I may have to do something over here. So y'all look while I do this. Ooh, look at there. I got it. Numeric response. Okay, so what you're going to do is you're going to put numbers into your deal. I numbered every carbon up there. If you think that there is only one chiral center, you will just put that number in. If you think there's two chiral centers, you'll put two numbers in and put them in numerical order. Okay, if you think there's three chiral centers, you will put three numbers in your clicker in numerical order. If you think there are 8 chiral centers, you will put 8 numbers in your clicker in numerical order. 1, 2, 3, 4, 5, 6, 7. I got one already. That's pretty good.
All the groups have to be different.
Yes, all 4 groups have to be different. And you got to look at the whole molecule. Okay? So do each number in turn is how I would do it. Okay? Approach the problem. Do each number in turn and decide, is that chiral, yes or no? Is that chiral, yes or no? Okay? And just only tell me the ones that are chiral. Okay? You have to break down and make a guess and nothing else. I know there's a lot to guess from. So instead of going A, 1 and 2, B, 1 and 3, C, 1 and 4, D, 1 and 5, all the possibilities, I came up with this. She's not sick, though. You would know if she was sick, would you?
Yeah, probably. I talked to her yesterday, but she wasn't at our house last night. She was at her mom's.
Oh, well, it wasn't bad weather. Okay, I'm up to 20. Is that everybody? I was thinking it should be 21 or 22.
22.
Okay. I might just pick something. Oh. Yeah, I forgot about that thing. So look at all the possibilities that y'all picked. Okay. How did I get other? No idea. No idea. Okay, so let's look at carbon 2 up here. Do you see that carbon 2, why it's not a chiral center? Right. There's a carbon 1 and carbon 7 are both methyls. Okay. So look, like I say, look at the molecule. There's a hydrogen, there's all that stuff, and then there's 2 methyls. So it's not chiral. That's why 5 isn't chiral. What does it have 2 of? Hydrogen. Okay. Okay. Yeah, I'm gonna have to go. Okay, so if I say, draw me, see now I can say the word, draw me enantiomers, okay? You will find the chiral center, you will draw one enantiomer, and then draw the mirror image. Use a wedge for going out of the plane, slashes for going behind, and remember straight lines in the plane. And that basically, you will have drawn both of them, okay? What you don't want to do is start drawing them and start moving them all around, because the molecules are 3D and it's really easy to draw the same thing twice and not realize you did that. So that's why it's really good to just think mirror, mirror image. Okay, so here is 2-chloro. Okay, so draw me the mirror images, the enantiomer. Draw me the pair of enantiomers for 2-chlorobutane. So what I would recommend doing, and that's the one I've been showing you, is number 1, just draw the molecule and don't worry about the chiral part. Just draw the molecule and find the chiral center. Okay, so 1, 2, 3, 4. Okay, so where's the chiral center? The one with the okay, the chlorine on it. So I'm going to take that carbon, and that's the one that I'm going to worry about this stuff. It doesn't matter where you put the stuff. Okay, as long as you put the 4 things. What are the 4 things going to be that go around this chiral center? A what? A chlorine. What else? A hydrogen. A methyl. And an ethyl. It doesn't matter where you put it. Okay? Now, put your mirror. Okay? Now draw the mirror image. Like literally draw the mirror image. So here's a C, and here's where the H is. And here's where the methyl is. See what I did? I'm literally just drawing the mirror image. And then up here is my chlorine, and down here is my CH2CH3. And now I know that I drew the pair of enantiomers. Okay? That makes sense. You just put the 4 things on there. Okay. There's another way that you can draw them that doesn't use the wedges and the slashes, and it's called a Fischer projection. Okay? Emil Fischer is a guy who did a whole bunch of work with sugars, and he came up with an easier way to draw them because he didn't like drawing them like this. So he came up with the cross. Okay? The thing with the cross is that nothing is in the plane. Okay? It's like taking this and holding it like this. You have the top and bottom are going back, and the sides are coming out. This is the carbon at the cross. Okay? The carbon with the cross, it only gets done for chiral centers. Okay, sugars have a whole lot of chiral centers, and that's why they started doing these for them. The main sugars, I should say. Okay, so this is him in 1891. I'm really throwing my molecules around today. Okay, he got the Nobel Prize in 1902 for all of his work. I never met him. FYI. No carbon is written in at the crossbar. If you write a carbon in, okay, and you write it like this, that does not mean a Fischer projection. It's just flat. It's not showing you any kind of stereochemistry or chirality. It's not showing you anything. So if you did this, if I said to draw me the pair of enantiomers and you drew it like this, you get the big X, okay? Because that's not showing chirality. If you want to do it with the Fischer projections, then you have to use the cross. Don't write the carbon in, okay? And so if you did this, okay, and then you did this, you would have drawn the pair of enantiomers. You got to remember, though, what it means. The sides are coming out, and the top and the bottom are going back. Nothing is in the plane. Okay, that's what that means. Okay, we only write the crossbar for asymmetric carbons. Well, let's not worry about that yet. If there were more than one. Okay, now what if we wanted to talk about only one of the enantiomers? Well, we had to come up with a way. I love how I say we when I had absolutely nothing to do with that. They had to come up with a way so that they could designate them. And that's called absolute configuration, where the groups are located absolutely. This is their arrangement in space. It's not liking me. Look at that. What did y'all do? All right. Look at this. We'll just start that slide over and see if it works. There we go. Okay, there is a system to use to figure this out, and we're going to go through the system today. Okay, it involves assigning priority to the different groups. Okay, and looking at where they are in space. So you really have to get in the spatial mode. Okay. The groups are going to be assigned priorities around the stereogenic center from 1 to 4. Okay. You orient the molecule so that the lowest priority group is away from you. So you would hold it like this. Okay. So 1 is highest priority, 4 is lowest. That's important. So I'm going to hold group number 4, and then I'm going to look at the other 3. Where are they positioned? Okay, I'm going to go 1, 2, 3, or 1, 2, 3. Okay. If it goes clockwise, that's rectus, which is R. Okay. If they go counterclockwise, it's sinister, which is S. Okay, you remember hearing that left-handed people were bad? That's like an old thing. They were sinister. That's where that's coming from. Isn't that funny? Okay, so you're going to label all these 4 groups, 1 through 4. You're going to grab number 4. You're going to look at it like a bouquet. Okay, and you're going to go 1, 2, 3. They're going this way. It's R. If it's 1, 2, 3, and they're going that way, it's S. Okay, we're gonna do them, just hang on. All right, so here is the 3 groups going clockwise. So what is this one? R. Okay, here are the 3 groups going counterclockwise. Okay, so it's going this way, that way. I couldn't make the arrow do that. That's counterclockwise, that's sinister, that's S. Okay, now how do we know what's 1, 2, 3, 4? Okay. Okay, the rules that we're going to use were developed by Cahn-Ingold-Prelog. Okay, those are the guys. I didn't meet any of them either. Okay, and these are their priority rules. The groups are ranked in priority by atomic number at the first point of difference. So if you have a hydrogen and a chlorine, which one is higher, hydrogen or chlorine? Hydrogen and a chlorine, that's what you're comparing. Which one's higher? Chlorine, because it has a higher atomic number. Hydrogen is always going to be less. I know. You don't have to have a hydrogen though. Higher atomic number outranks lower atomic number. Higher outranks lower. Okay? Did you get that? I thought there was another thing going to show up. Okay. When 2 atoms are identical, you go to the next atoms attached to them and compare those. The first point of difference wins, and that is a key thing. First point of difference wins. So you're going to start at your chiral center and you're going to step out and you're going to compare all 4 of those atoms. Okay? And then if some are the same, then you're going to compare those. You're going to take another step. It's like you're walking out from your chiral center until you get to where it's different. Yes. Because you could have a methyl and an ethyl, right? So we're looking at a carbon and a carbon to begin with. That's the same. Now we're going to go out another step. So we're going to do them, okay? And that'll probably help clarify for you, okay? When there is more than 1 point of difference, okay? So like you could have an H and an O, and a C and an S, okay? And you have to compare those 4 atoms. Which one do you pick? You pick the biggest gun, okay? Because if you pick the O and the C, the O would win. If you pick the S and the H, the S would win. So you always pick your biggest gun. So if you have an H and an O, the O goes out, okay? If you have an S and a C, the S goes out. So who's higher, S or O? Which is higher atomic number? Go ahead, look at the periodic table. It ain't going away. S. Okay, so that group would win. We'll do a couple like that, so that'll give you practice with it. Okay. Okay, yeah, biggest gun. Just remember, always use my biggest gun. I want to live through the experience. Okay, evaluate substituents 1 by 1. People have told me, look, Dr. Wadman, if I add all of these atomic numbers and all of those atomic numbers, that one's higher than that one. And I'm like, okay, how about this one? And I'll show you an example and where it won't work. You just got to learn the stepwise method. It's the only thing that works, okay? Trust me, if there was an easier way, I would tell you. Okay, now what if you do the multiple bonds, okay? Because you won't have as many atoms. So we're going to swap those and fill in the multiple bonds so that we have the same number of atoms to compare. That's all that's for. The multiple bonds are still there. So you'll see, we'll do something like that too. Okay, put R or S in front of the name in parentheses. It's a capital R in parentheses. Capital S in parentheses. Just like we did cis and trans. Okay, except those weren't in parentheses. They were just in italics. Okay, so here is 2-butanol. Okay, which one is this one? Is this one the R or is this one the S? So what we're going to do is we're going to prioritize the 4 groups. So you start at your chiral center, and what are the 4 atoms that it's attached to? H, O, C, C. Everybody see that? Let's see what I have on here. Oh, I just have the other one. Oh, I think I wrote it all on the board. Okay, so here it is. I'm going to redraw it so that you can write it all down. I have it this way. Okay, so I have almost the same colors. I have pink instead of orange. I'll have to get orange. Okay, so I have C, C, O, and H. Those are the atoms that I am comparing. Because those are the ones directly attached to here. If you're lucky, they're all 4 different and you're done. Okay, can you tell me who is number 1? Oxygen, what? It has the highest atomic number. Okay, what else can you tell me? Who is 2 and 3? Well, we don't know yet. They're the same. But who is 4? 4 little hydrogen. Okay, now to decide who's next, what is attached to this carbon? 3 what? Hydrogen. This is where you're going to have more than 1 atom potentially to compare. Okay, what's attached to this carbon? 2 hydrogens and a carbon. So we have a C and 2 H's. Okay, and I know you probably know which is 2 and which is 3, like really fast, but I want to make sure you get the process so when it's not so obvious, you can do it. Okay, so I'm going to compare this C and this H because that is what's different, right? Now we have a point of difference. So who's 2? The ethyl's 2. This group is 2. And so the methyl is going to be 3.
How does that work?
What?
Because you can't skip to 2 and then go to 3 and then make 4.
Oh, hang on. We're not done. That's the first part.
Okay.
Okay, hang on. Okay, now, since I used purple and this is the pink and this is the green. Oh, look at that. I have to say the right one. Okay, so I'm going to hold number 4 away from me. And yeah, bond broke. Okay, I'm going to hold it away from me. Okay, so now here's 1. Here's 3. And here's 2. That's how you finally get to S. You can't do it from this. You have to take this and get it so you're holding number 4 away from you. Okay? So when we do the enantiomer, now we know it's going to be what? It's going to be R. Because if you have one that's S, the enantiomers are. Okay? But let's do the rotating part because that's the hardest. Okay, so here's this molecule. Here's the methyl. Here's the OH. Okay, so this was 1. Okay, this was 2. This was 3. And our 4 little hydrogen was 4. Okay, so let me get it so it's the same. Okay, I want, yeah, kind of weird. Okay, so here's 1 and 2 in the plane. Here's 3 coming out. No, I have 2 and 3 backwards up here. Okay, is that what you were trying to tell me?
Yeah.
Okay. That makes more sense. Okay. Okay. I still have really messed up my poor little molecule. Okay, so here's 1 and 3, right? Here's 2, and here is the white. Okay, so these 2 are in the plane. The green is coming out, and the white is going back. If you use something like this to help you do the rotations, it's important that you get this in the same orientation as the molecule on the piece of paper. Okay, I'm going to grab number 4 and I'm going to pull it away from me. So we're going 1, 2, 3. What is that? Clockwise. So it's on. You get, is it sinking in a little? It's going to take a little practice, and for the test, I'll let you bring one of these. You can make it with gum drops or pipe cleaners, but when you take the MCAT and all that, they won't let you. Okay, so you might want to practice doing it without it, and then do it with it, and then see how you're doing. Okay, the MCAT, the DAT, the PCAT, all those lovely tests, they won't let you bring that in, that crutch. Okay, so now this is how you put the name. You put the S in front in parentheses. Have you seen R and S yet when looking things up for lab? You did the TLC analgesics lab, didn't you? Anybody run into it in those? Because some of those are chiral. There's some other ways they can be designated. So we'll get to those. I was hoping to do this before you did that lab, but okay. All right, so we're gonna do like a whole bunch of these next time. So if you have something, bring it and see if you can get it. Okay. Ooh, and I'll put up your homework, and because there's no rest for the weary or the wicked.
Let me know about it.
Oh, okay. Thanks. Does it say everybody's name?
Yeah, but then
You're the only one in my class.
Yeah. What's her location? Her house in Gordonville.
I wouldn't do it for
Yeah.
either.
Color.
What's assessment testing day?
Well, I mean Wednesday.
Oh, okay.
The
Okay.
last time we had class.
Okay. All right. Yeah, it's in my office. I just don't carry them around. I have so much to carry around. It's ridiculous.
still in there, Robbie.
Oh, okay. We all have fun. I'll see you when you get back.